We're going to get started now because I think that people have stopped coming in. Um, were you here, was anybody here last year? Do you remember last year? Okay. You might remember this, maybe the rest of you don't. But last year, while this conference was going on, while I was up here on this stage, London, well, the whole of the UK really, was actually having a lot of difficulty. There were some very high-profile hacks going on. The Co-op, a big, those of you who are not local, it's a big sort of supermarket chain. They had been shut down by a ransomware attack. They limited the damage because they unplugged all of their computers as this was taking place. Marks and Spencer's was not so lucky. They didn't realize what was going on. They lost all of their data. They were very seriously impacted by it. They're still suffering from that now. The Co-op has largely recovered. But Marks and Spencer's, they did very badly out of it indeed. They effectively lost everything. At the same time, the same people who were launching these attacks also launched an attack on Harrods. And since hardly anybody can afford to shop at Harrods, nobody even noticed. But nevertheless, this was a very significant attack. It's rated one of the more serious ones. And you all know what happened after that, don't you? Jaguar Land Rover got absolutely hammered. And this was not just one retailer. This was the entire factory, the entire supply line. Hundreds of companies were affected by that. This was just over the space of a week or two in this country this time last year. You remember this, right? This is not news to you. Now, this represents a tip of the iceberg. If we look at what's happened over the last year, since May 2025 and now, we have had a number of really significant hacks. This is the UK alone. It depends on what sort of definitions you use, but there have been somewhere between 10, this is highly critical attacks, and 25 nationally significant attacks. Yeah, that's the term, nationally significant attacks in the UK in the last year. On that basis, on that scale, there have been possibly 100 significant attacks. Now, significant means serious damage to money, to safety, these sorts of things. 100 in the UK in the last year. These, as I say, are just some of them. And these, if you look through this list, you remember all of these from the headlines. None of these are surprises to you, are they? If we widen our scope to Europe and to the world, these attacks are going on absolutely continuously. The numbers of attacks worldwide, they seem to be about 10 times these numbers. There have been about 1,000 significant attacks worldwide. We're looking at between 150 and 300 critically significant attacks around the world. And to give you an idea of the sorts of things that there are, here I've got a list of the top 100. This is the first 30 of them, and you can see the kind of groups that it's been broken into. But so these are the most critical ones. These are the really serious attacks that are affecting national infrastructure or fundamental safety. But if we extend this even further, these, you can't even list the attacks, but what you can do is look at the kind of spaces that they're going into, and there isn't even room on this screen to fit them all in. These attacks are going on all the time, and they are causing real damage. Now, just to calibrate the room, how many of you are responsible for security, perimeter security, resilience? Okay, cool. So the rest of you are developers who are not. Have I got that right? No, I haven't. You are responsible. And we're going to be talking in a moment about why. But yes, everybody in this room is responsible for protecting your employer, your business, excuse me, even your own assets, your own personal assets. And so what I want you to do is I want you to leave this room, if nothing else, with a security mindset. I want you to think about these attacks going on. But all of these attacks that I've shown you, that first screen, these ones here, those 150 critical attacks, nationally critical attacks, all have something in common. What they all do is they target the same thing. They all have the same objective in mind. And that objective is the data. Why? Why do they all go after the data? Well, Willie Sutton, the famous bank robber, was asked in an interview, why do you rob banks? He says, because that's where the money is. Why do they go after the data? Because that's where the money is. Number one, everything that they want that's of any value lies in the data. They're not interested in your software. You go to all sorts of lengths to protect your data in your repositories. They're not interested in that. That's not an asset. That's just something that you use. All the value is in your data. A lot of those hacks, the purpose of the hack was to exfiltrate, or part of the purpose was to exfiltrate data, and then use those to launch more specific targeted attacks. When you get those phishing emails coming through, that's where they come from. They come from these large-scale hacks. And there's a whole ecosystem out there where you have these aggregators who will take stolen data, put it together, and gradually build up a picture of people. They will crack passwords. They will find out your family, your pets' names. They'll find out all sorts of things about you so that they can personalize these attacks. So all the money is in the data. There's something even more important. And that is the very soul of the business lies in its data. The data is how the business knows who it is when it wakes up every morning. The data, it's the sense of identity, the sense of continuous personality that lives in the data. That lives in the data. If a business wakes up and it has no data, it's been lobotomized, literally. This is what happened to Marks and Spencer's. This is what happened to Jaguar Land Rover. It had no memory of itself. It had no view of reality. And this really matters. So that means that the whole point about ransomware is to place that data beyond use, beyond the use of the business, and then try and ransom it back before the business itself gets so badly damaged that it can't. And in fact, one of the things that we know, we saw Marks and Spencer's did survive it. We saw the Co-op survived it. We saw that Jaguar Land Rover survived it because they had massive influxes of government money to keep them afloat. But these are the big people. These are the people that are too big to fail. For every one of those, there's 1,000 who don't survive. And when you have one of these attacks, which is attacking your data, it is always an existential threat and is usually fatal. That's how serious this is. So, the things that we value as developers, the things that we value in our companies, seems to be the code that we're writing. But the code is ephemeral. By God, it should be ephemeral because you should be refactoring it and cleaning it up all the time. But the data, the whole point about the data is that it persists. It is not ephemeral. It's persistent, and it's where all the value in the business lies. And again, I want you to take that thought away as well. Okay. We talk a lot about data. Every programming team you go into has an opinion about what data is, how you should store it. People talk about the benefits of ACID versus base data management. People talk about the benefits of SQL versus NoSQL. And the thing is, there's no resolution to these arguments because actually both sides are right in every one of them. But I'm going to offer something here. I think that there is something which needs to be true of a database without which it is not worth the electricity you spend on it. And that is, it needs to be complete, correct, and confidential. Your data, there needs to be some point in your data where you have an absolute source of canonical truth. The things that you think are true of the world, of your business, of your customers, everything. You need to have a source, a canonical source of truth, and you need to be able to rely on it. So that's what this means. You need your data to be complete, correct, and confidential. Okay. Excuse me. Now, when somebody is trying to attack your data, when somebody is trying to get into your system, and they're trying to reach your data, they are trying to compromise at least one of those. They are trying to exfiltrate data. They want to know what you know. They want to be able to inject false data. And the thing is about injecting false data is that if you don't know what the difference is between the real stuff and the counterfeit stuff, you can't tease them apart again. So you lose your view of reality. And so these sorts of attacks will literally change your view of how things work. And so there are attacks where people will go in and modify the central heating system or modify the lifts to make the office unlivable. And that is an example of injecting contamination. And of course, the third thing is to ransom it. You take the data out of use, you take the data beyond access, and then you ransom it back. And what that is doing is making sure that it's no longer accessible. So in each case, the purpose of a hack is to compromise one of these properties. But without all of these properties, your data is worthless. Does that make sense? So, how do we manage that? How do we make sure that our data is protected? We toughen up our perimeter. We make sure that only the people that we trust get in, right? No, why not? I'm sorry? Absolutely. As you hear it, once you're in, you're not protected. You see, this is the problem, that a strong perimeter, it doesn't really keep the bad guys out. I'll show you why that is in a moment. Doesn't keep the bad guys out, but what it does is it traps him in. It gives him free rein once he gets inside. The idea is, behind toughening up perimeter, is that if you know who's getting in, if you can monitor what they're doing when they're inside, then you can keep an eye on who's doing that. So, in the case of the Marks and Spencer's hack, the way they got in was they phoned the help desk and they said, "I've lost my password. Can you help me log in again, please?" And the help desk, which was in India, paying minimum wages by Indian standards, said, "That's what we do for a living. Absolutely, we'll help you." Do you know what? They had spearphished the guy who owned the credentials to the Active Directory master file. And they were in, and they had complete access. The truth is, the bad guys don't come through your encryption. They don't scale the castle walls. They come in through a door or a window which somebody has left open almost every time. So who are these people that are coming in? Well, let's move on. This amazed me when I found this out. We were working on a very sensitive project doing remote oil well management across the world. And we knew that this was a serious problem. And so we called in a guy from British intelligence to help us build our security. And this is what he showed us. Nearly every attack that's ever going to happen is going to involve some element of an inside job, to a first approximation. This is somebody who has either been tricked by a spear phishing attack, or they've come in drunk, or they're disgruntled and they want to get their own back on the company, or they're getting ill and losing their mind. And there are all sorts of reasons why sometimes it's down to pure malice, but there are all sorts of reasons why every one of these attacks, to a first approximation, is facilitated by somebody whom you already trust. That's why the perimeter is no good. So what this chap said was that, if you only take one thing away from this whole conference, it should be this: the bad guys are already inside your system. So that means that your systems, your software, and in particular your data, should be prepared to defend itself against intrusions. If you have done this correctly, I'm not doing this now, but I've got another talk about how to build inherently safe architectures. But if you have done this correctly, you can chaos monkey your perimeter into rubble, and you can still feel safe. Just a quick poll: who would be prepared in their installation to switch off the firewalls and just let the system run? Didn't think so. But that is what security needs. If you believe this to be true, and all of the evidence says it is, then you cannot rely on your firewalls. Does that make sense? There's the data itself which has to defend against malicious activity. And our data doesn't. Pretty much none of it. And I'm going to show you why. Let's go back in time a little. What did data look like through the development of the computer age? Back in the 60s and 70s, data processing looked like this. Now, has anybody ever worked in a room like this? Okay, cool. So you're going to back me up. Everything I'm going to tell you is true. What you have is a number of boxes which are actually not very complex boxes. These, by modern standards, these are very, very simple computers, and you can tell from all the switches on the outside that actually they've got very simple interfaces. This guy's working on a teletype. He's sending in job commands. But what you can see is dozens and dozens of tape drives. All of the data resides on tape. Now, tape has a number of really interesting properties. Excuse me. It is cheap as chips. If you need more data, then if you need more storage, you just buy more tape and you store them in the library. And this is what these libraries used to look like. The only thing that's not realistic about this picture is that the tape-off never moved fast enough to get blurred on the camera. But apart from that, that's what they looked like. You just buy more tape, you store it, and it's very, very durable. These tapes would last 100, 200 years if you left them. And people still use tape for archival storage now. You would have multiple tapes loaded onto drives like this. And so you would set up, you'd create a job and you'd say, so load that tape, load that tape, load that tape, and then each of these tapes would spool independently. So you'd read from this tape and then write to that one, read from this tape, write to that one. And there were all sorts of interesting algorithms and interesting software running inside here that would perform business operations like merging or payroll runs or whatever it was. But fundamentally, the entire input to this process and the entire output was onto the tapes. Excuse me. By their nature, tapes are serial devices. They're hundreds of meters long, right? But also, because of the way they were laid up, they were append only. So there was indexing, and you were able to sort of scoot through the tape quickly, and occasionally you could scoot backwards. But generally speaking, you had read tapes and you had write tapes. It was almost impossible to rewrite records in the middle of a tape because the records were variable length. They looked very much like paginated streams of text, like what we would call a serial file now. But the point was that these tapes were append only. And that was what ran the world for, frankly, decades. They were slow, I'll admit it. There was 2 levels of indexing. You had to pick the right tape, put it on the machine, and then scoot to the right point on the tape. But fundamentally, once you'd done that indexing, it was a very, very shallow directory hierarchy. But then something happened. IBM invented this. This is a disk drive. Now, the point about the disk drive is that you can see that you can have a hell of a lot of disks mounted on it at once. This was much more compact, much cheaper than those tape drives. You can see what he's holding here. The idea was that these disks were replaceable in the same way that you would mount a tape on a drive. You'd mount a disk on the spindle. And so you could have 100 disks all spinning, each with their own head. There were slightly more random access. But the trouble was that when they built this, they still had this underlying model of tape. The things that were controlling this were the same tape-based operating systems. So as far as IBM was concerned, this was just better tape. In Henry Ford's sense of people want better horses, this was better tape. And it was better tape. And this was a very successful invention. Over time, these things shrank down to a thing like this, where you would move whole packs around, and then eventually it turned into what we now call primary store. There was no concept of primary store in the days of tape. There was no concept of primary store here, but it eventually turned into primary store. So far, so good. But then, the next thing happened. This chap came along. This is Frank Codd. You know who he is? Okay. Right. Frank Codd said, there's another way of thinking about data. He called it relational data. And he said, the point about relational data is that you don't need to have all of this denormalized data on spanning enormous volumes. You don't need to have all of this duplication. You can keep it small. Because we know that these tables, these records are the same size, we can place them. So we can randomly read them. He created, first of all, an idea of a manifesto about what this is. And then he eventually did a load of work building up a thing called System R, which IBM absolutely hated. Because they said, but it's not tape. It doesn't work like tape. Our expertise is in tape. And actually, although they let him build the project, they took him off it, they put obstructions in the way, they did their best to kill it off until Larry Ellison said, oh, that looks interesting, and created Oracle on the back of it. But what this did was it created erasable data. The whole point of the relational model is that you could go in and rewrite. This is the moment that CRUD was invented. CRUD is create, read, update, delete. And that is where everything went wrong. Let me show you why. Let's talk about the model. Let's try and talk in the abstract about data. Let's look at the file and tape model, first of all. We've got a source of data. We've got a source of transactions, a source of events or something. And what we do is we place the results of that into various files, various records, various blocks. Okay? And we need to do this in a synchronized manner. And then when we read them out, we pick one, and the data that we want is already sitting there. So all of the transformation that we need to do has already been done at this point. If we want synchronization, if we want consistency between the various bits of data, we have to do it in this process. And if one of these things fails, we lose the consistency. Now this is the model behind tape. This is the model behind serial files, text files on disk. This is the model behind quite a lot of NoSQL databases, because the whole point about NoSQL databases is that you're storing everything denormalized in the form at which you need it at the point of use. Okay? So this is the original model. Anybody who tells you that the NoSQL is the future of data, well, it might be, but it is more definitely the path, the history of data. But what happened when we created relational data is that this relationship changed. What happened was we still had these data repositories, but they were slightly different to what they were before. They were now random access, which means we still need these synchronized reads, these synchronized writes. It's just that now these are totally dependent on each other. If there's an inconsistency, it's not that two tables disagree with each other, it's that you've broken your database. But the payback for this is that these are much smaller chunks of data. You're not supposed to have any kind of duplication from one table to another. So when you're reading data out, you would typically look at two or more of these tables and combine the data in some way to get the result that you're actually asking for. But this here is the point at which we are trying to get these various things in synchrony. And something that goes wrong here, it's going to poison our database. It's going to make our database contaminated, unusable. We can't tease the things apart. Now, in the old days, and some of you will remember this, we used to do that process using stored procedures. The actual fact of doing this computation and keeping all of these things consistent was done by the database itself. So you'd say to the database, this is the event that's happened, and then the stored procedure would do whatever was necessary to update the tables, and that whole process either succeeded or failed. The only control surface was those stored procedures. The client didn't have access to the tables. It only had access to the stored procedures and the queries. But we don't do that anymore, do we? We do ORMs. And we do ORMs because, well, actually because it suits the way we use version control better than stored procedures do. Stored procedures in version control is really hard, and the reason is that version control is supposed to manage the variability, the way your code changes, but the whole point about a database, as I said before, is that it's persistent, and so those two models are colliding. And the trouble is, we've given away a huge amount of reliability in that, because now, if a bad guy gets into this, he can update those tables independently, bypassing what the stored procedures that would have been in place. But there's an answer. The answer is CQRS. Now, what happens in CQRS? You know what? Does anybody not know what CQRS means? Okay, it's command query responsibility segregation. It means that in the same way that before we had a query on the output, we actually have a command process on the input. And they work from different models. They work, the kind of ideas that exist in the command side are different from the ones in the query side. So for example, an order comes in and you need to update your financial records, you need to update your warehousing records, you need to place the orders, you need to create an order for delivery. All of that happens inside the command processor. Now that means that these things, before in the tape version, in the serial version, remember the things that you're storing are in the form of the query. So you have to do a lot of transformation to get it into that form, potentially. In the relational model, you've got to be able to serve a query efficiently. So actually, the data is more like the query, it's more like what you want to know than what's gone in. And the logic behind that, of course, is that you query more often than you write. In CQRS, it works differently. We can actually make this more. It doesn't need to be like the query. It doesn't need to be like the command. It can be different to either of them. So that's why these have moved over to this side. But again, you still have this combination process on this side. But in each of these cases, this data is updatable. This data is deletable. That is the reason, bypassing these is how the bad guys exfiltrate your data. Tampering with these is how the bad guys contaminate your data. And ultimately, if they've got access to the volumes, to the files themselves, or to the volumes they're sitting on, that's how they take it away from you. So this is where the problem comes from. It's from the UD part of CRUD, I claim. But this is not how we've stored data for most of history. This is how we've stored data for most of history. Do you know what this is? It is a cuneiform tablet. It's about 5,500 years old. It came from Mesopotamia. Do you know what it says?
It's the one I know. It's basically an inventory of farming supplies or something like that.
Yeah, this is basically a tax record. This is the various locals who have brought ox as a sacrifice to the temple. This is some of the very earliest writing that we know on Earth. It is not poetry, it is not love letters, it's not history, it's accounting. And the process by which it was made was there was a tallyman sitting outside the temple, and as each person turned up with the ox, he recorded his name by pressing a tool into the clay and then marking his tally. These are the tallies over here. And then what did they do with it? They baked it. I don't know, it was intended to last 5,000 years, but it was intended to last because these things were collected together in libraries, in basically tax offices, and they were referred to. They had effectively accountants who would go through these and say, actually, we don't need to go and count the cows. We know how much value we've earned. This is the beginning of accounting, and it is permanent, designed to be permanent. This is not updatable after the fact. These things were actually signed by the collectors, by the way. It's not updatable after the fact. You can't delete anything. I mean, you can break it, but the damage is obvious. You can't introduce anything new because of the tools. In our terms, this is an append-only permanent record. This is what our data should look like. Now, we are not going to build clay storage devices, right? I get that. But what happened next? This happened. This is a ledger from 1890, I think. For quite a lot of time, in fact, pretty much since the Romans, and I couldn't find any examples of Roman ledgers, but this is how accounts were done. Every company had a set of books. When I started in business, I had paper books like this. My handwriting was not as good as this, but I kept my accounts in books like that. And I want you to notice several things about it. These are bound books. If somebody tears a page out, it's obvious. That can't be hidden. What's less obvious is that these were written in ink. And in fact, they were written in a special kind of ink. It's been known since about the 1600s as registrar's ink or ecclesiastical ink. This is not like the ink you put in fountain pens today. Those of you who still use fountain pens today. This actually creates a chemical change in the paper. You can burn the paper and the ink is still visible on it. Okay, right now they use it for things like death certificates and marriage records and things like that. The things where they're giving you a piece of paper which might have to last for decades, they still use this same kind of ink. This is a very good piece of, a good example of a ledger. Look at the quality of the handwriting. This is designed to be looked at. Everything about this is speaking permanence. Once you've written a number down, you've written it. And you can't remove it again. You can't erase it. You can correct it. You can cross it out and write something beside it. But the fact of the correction is visible. Here's another example. This is a more tradesman-like version. The handwriting is not as good, but it still follows the same principles. You can still see it's dated. This is from, 1877. It's dated. It's very clear what it is. Again, it's still bound. Everything about this is intended to be permanent. And we used these routinely up until the end of the 70s, early 80s, when computers started to take over. Now, you've seen the examples of this. You've seen the heritage of this on your bank statements. It's a list, very much like this, of the money that's come into your account, the money that's gone out again. And if you pay in a check, it appears on your bank statement. And if the check then bounces, what happens? They don't erase it. They don't even put a line through it. They write underneath a contra. They say, this didn't happen. And so it balances, but they're telling you why that payment has been taken away. And they're telling you why that deposit has been taken away. And they're telling you when it was taken away. And they're telling you what the effect is. All there in the ledger, because the ledger is a list of what actually happened. And it's in a permanent form. Is this looking at all useful to you? This is complete, by definition. It's correct. It is actually checkable. What you've just seen is examples of double entry accounting, and double entry always has to balance out. So if there's anything wrong, you can tell. And it's confidential. You need physical access to the book to access it, to read it at all. I claim, and this is a big claim, but I claim if you want a source of truth in your organization, if you want your data to represent a source of truth, it should look more like this than it does look like a disk. Would you agree with that? You're not convinced. Well, I'm going to show you why. Because there is another way of building a database that we haven't looked at. It's this. We start off, as we have before, with a source of truth, a source of events, a client of some kind. And what this does is it records events that have happened. Money has come in. Money has gone out. An order has come in. An order has dispatched, whatever it is. But these are events. These are things that have actually happened. And we place each event into a single record, a single source of data. Now, the point about this is that all we ever do is append, just like you saw with the tape, just like you saw with the physical ledgers. All you can ever do is write onto the end of it. And there is no consistency requirement because what you're doing is recording actual facts, one after another. So how do you use this data? Well, in the same way that you use the ledger. Some people are going to use the ledger to say, how much money do we have in the bank? Some people are going to look at the ledger to say, how much profit have we made? Some people are going to look at the ledger to say, who owes us money? The thing is, there's lots of different questions that you can ask of these ledgers. And this is true with these computer ledgers as well. So what we now do is we create a process which distills from those records the data that you actually want, the actual value, the actual information that you want. So now what we've done is we've taken this data, remember, over that projection, over that development, these data files have moved further and further towards the nature of the things which initiate them rather than further away. So in this case, we have to do processing to answer the question, but we can do different processing to answer a different question. So we can ask lots of different things of this data. Now, what happens if the format changes? What happens if what we're expecting of here changes? What happens if, for example, we can now handle accounts in multiple currencies, or there's a distinction between credit accounts and cash accounts? Well, if you're working with a relational database, you've got to change the schema. And then you've got to migrate the schema, and you've got to get the data that you've got in the old schema migrated into the data that means the same thing in the new schema. But in this, you don't have any of that. You change these, but these are ephemeral. These are what go in your version control. This stays permanent forever. Because the fact of what happened is not changed by your developing interpretation of what that even means. Does that make sense? Okay, this is called event sourcing. And it's based on an event model. There is no UD in this. There is no possibility to update or delete. There's not any way to update or delete, even if you have access to the volume, as you're going to see. Because actually, all it will do is append. So what does that actual data structure look like? What we do is we first of all create a stream. We create a stream of events which has something in common with each other. And as you saw from before, what's happening is the events are coming in from the client, and each event is being added to this list of events, one after another. These are connected together cryptographically. You can't change one. You can't introduce one. You can't delete one, because if you did, the rest of the chain would break down, like cryptocurrency chains. It's a similar sort of technology. What's this? The creation of the event, or the creation of the event stream. That's another event somewhere else in the system. Each of these things, if we had time, then I'd show you this, but each of these internally is encrypted, and they can be encrypted with different keys or different key families. So what we could have here is personally identifying information from dozens of different customers, and you can see the records, but you can only read the record if you have the decrypt key for that particular customer. So this is very reliable. So you can see, without going into too much detail about this, you can see that what's going on is that we can create, this is correct by definition. We know that it can't be modified, and we know it stays confidential, because unless you've got the keys to access this, and to access this, and to access whatever constructed this, You can't read any of it. Is this sounding exciting? Is it sounding a slow way to read a database? In fact, let me finish putting on. Each of these things contains basic information. It's got an ID number so you can find it if you need it. It's got a type. It's got some message. Basically, this is the kind of structured data or semi-structured document type data that you'd find in a NoSQL database. But it also has a cryptographic link to the predecessor, and it also has a timestamp so you know when it happened. And these are provided automatically by the system. Now, when you want to read something out, you start at the bottom and you work your way up. Let's suppose you want to know how much money you've got. You don't need to know who the customers are, right? All you need to know is how much money you received from each one. So you go through here, adding up the receipts or the credits or the debits on each record, and then that gets aggregated into the state, into this ephemeral materialized state, which you actually deliver to the client that's querying it. Now, you can do this with any database. You can do this with SQL databases. You can do it with NoSQL databases. My advice, if you do it with SQL databases, is do it in stored procedures, because you absolutely don't want to expose the tables to the client software, because that's where it's accessible. You've got to hide this inside the database. If you're using NoSQL databases, you've got to put it in its own service, inside its own firewall, so again, nobody can see in. And one of the reasons for doing this is that just having access to that database doesn't give you anything at all. It's just gibberish until you've got the keys to start traversing it. So this produces something inherently safe and inherently protectable. But it can be a bit of work to put this through something like a SQL database, because actually the relationalness is not what's important. There's almost no relationalness in this structure. So actually all you're doing is using a database that you're familiar with. There is, as far as I know, only one database which really does this naturally. So you can do this in almost anything, but there's one database which does this out of the box as of design. It's called Current. For disclosure, I am not connected with the company. I'm getting nothing for this. They don't even know I'm here. This used to be called Event Store. That was Greg Young's thing. But it got taken over by Current and productized. And Current is now offering this as a cloud service, as a self-hosted service, and even as something that you can run on your laptop for testing. But it is an event store by design. It's got all the cryptography built into it. And what I suggest is download the demo and play with it and get yourself an idea of how this works and see what the capabilities are. But this is absolutely unhackable. What happens if the bad guys break into your system? What happens if they gain access to your clients? What happens if they start injecting dodgy data? Well, okay, the aggregators are going to show the wrong results until you have a chance to go back, because all of your original data is still in place. You can't delete the iffy records, but you can contra them. And so now the aggregators will take them out again. And if you've done your job right, you should be able to find them. You should be able to find who created the record, where they were, all of the metadata that you use to separate the iffy stuff from the real stuff. That should be right there in the record. So it's easy to go through and contra them in a mechanical manner. So they can't contaminate your data. They can't steal it unless they've got access to the keys. And they can't place it beyond use because actually they don't even have deletion rights. They don't even have update rights. They don't have access to the thing itself, because all they've got access to is creating a new record. Do you want to ask me anything? I've got 5 minutes left, but I've covered pretty much all that I wanted to cover. Yeah. In theory, yes, it is. And that's the commonest objection to this. Sorry, for the camera. The idea of having to traverse every time. You do it once, you do it again, you do it again. The thing is that every time you're doing it, first of all, you're looking for different kinds of data. So if we do it once and we say, what's our business with this customer, that's a traverse. If you do it a second time, but it's a different customer, obviously you've got to rematerialize. But if you're going to, if you're asking, what was my net worth at midnight, at close of business last night, you've got to do the traversal, obviously, but then you don't need to do it again. You can cache it. And there's a process that's built into this called snapshotting, where you actually create those snapshots as an event stream of its own. So all you need to do is to go back to the previous snapshot and then traverse from there to get the current state. But it also gives you the chance to validate those snapshots, because that snapshot is everything from that snapshot to this one, so you can check each one. And in the event, because each operation is very simple, the overhead is surprisingly less than you think. It's also absolutely predictable. And that's the drawback with SQL. You can never tell, in theory, how much work it's going to take to satisfy a query. This, it's always exactly the same. You happy with that? Okay. Anything else I can tell you, folks? Yes? Well, in that case, you have much bigger problems. But and the answer to that is a talk which I'm not doing here, but I am doing next week, which is how to build your architecture such that that can't happen. The model for this is how a credit card fulfillment happens, where basically you've got a credit card intermediary, the shop speaks to them, gets a nonce from them, they provide their own form in there, and then they get received. And then the intermediate speaks to the credit card clearing companies. But at each point, nobody has any usable data that they can use to game the system. And even if you get access to it, there's nothing visible there. So if you got access to the intermediary, you couldn't interpose yourself to do any damage in there, because the data that you're dealing with is all meaningless. It's all nonsense. So that's the short answer to the question. The long answer is next week.
Does this not mean we have to trust current, right? I mean, in the same way that we might have question marks over trusting AWS in the long term, you have to trust that as a cloud provider to not be breached, to not supply chain risk.
Yes, but number one, everything is cryptographically secured. And you can own the keys. And number two, you don't need to trust them. It'll run in a container, or it'll run on your desktop, or you can provision it yourself. So you don't have to trust them. You can provision your own. You can trust your own provider.
Yeah. Then I'm trusting wherever that container is stored.
No, because you own the keys.
That just means that nobody else can read it, but they can still destroy it.
Yes, you have to trust the provider not to let it get destroyed. But most people outsource backups because the providers are better at backups than anybody is, because nobody does the backups. Okay, we're almost out of time, so I just want to show you this. I'm Jules. I care deeply about reliability. I think that reliability and security are the same thing. The next talk I'm going to give in 10 minutes in this room is basically the introduction to that book. That book is available online. Go and help yourself. There's a free sample. If you want to know more about this stuff, there's 400 pages of it there. And I know nobody reads books, and certainly nobody reads 400 pages, but the book is right there. And that's all I have for you, folks.